Good morning and greetings from Würzburg, Germany. First of all, thanks for allowing me to participate in this community day, even when I'm not a local speaker. This is especially nice as I wasn't able to participate in the German AWS Community Day a few weeks ago. I want to start this talk with a discussion on what serverless means for networking. Afterwards, I want to give you some context at how we at EMnify provide cellular IoT connectivity. And finally, I want to explain you how we implemented AWS native IoT connectivity for our customers' IoT devices fully serverless. After giving you a short demo on how you as our customer can set this up, I will guide you through the orchestration layer that deploys all of this for you, again, built using serverless AWS services. Why do we like serverless so much? What advantages do we get from it? Besides higher chances that you get your talk accepted at events like this, when the title includes the word serverless, probably. Yeah, there are a couple of advantages, just to name a few. Yeah, we don't have to really take care about it. We just call an API and it hopefully works. Usually those things scale as needed. And if it breaks, somebody else fixes it. I think that's the best of all. So what does serverless mean for network enthusiasts like I am? Let me give you a bit of context about myself. I started with AWS in 2017 when I joined EMnify. Before that, I was a full-time researcher at the University of Würzburg on the topic of software-based networking, for which I also received my PhD. I have fun doing AWS certifications, especially the advanced networking specialty, which was also a real challenge. But back to AWS networking. If we think of networking in AWS, doesn't that have the same characteristics already as serverless compute services? I mean, my EC2 instances, my Lambdas, my containers, all of that can communicate, assuming I get security groups, right, of course. So yes, we usually assume that VPC networking is reliable, has infinite bandwidth, is secure, etc., etc. So would I consider, for example, a VPC peering already something that magic serverless? Well, actually not, I must say. I think that's more like running a cable from A to B. There's no real logic implemented it. I think of a bit more complex networking, more what we would call network functions. And I try to classify some of the AWS products. And it's for sure just a very rough categorization, and we can certainly argue about the details. From left to right, we see an increase of flexibility of control that we have over that service, and maybe also a bit, like I would say, yeah, the gap that it bridges that we would have to otherwise implement ourselves. Yeah, most prominent, maybe the NAT gateway, which I assume most of you have in use. And there are certainly reasons against it, but in principle, this relieves us from running our NAT instances. And just think of how complex it is to set up highly available NAT instances yourself. How do you replace instances for an update or for an increase in capacity? I think that requires a huge effort. Maybe the gateway load balancer that was introduced earlier this week could be really a game changer. I haven't thought it through, but maybe that would simplify such implementation by far, compared at least to the previous status. Nevertheless, going a bit further on the flexibility, Private Link allows to share a network load balancer and thus an application into a different VPC or even a different AWS account. Similar global accelerator, a network function, actually what others would call maybe a WAN optimizer. And then kind of right in the middle, I think, of the flexibility landscape, there's where I would see direct connect and site-to-site VPNs. This sounds rather simple, but this also provides managed BGP services. And have you ever tried to run a BGP daemon, something that you can even reconfigure on the fly via an API? In my career, I would say I haven't felt anything more painful and frightening to blow up everything, basically, than when I was dealing with Quagga. Similar, did you ever create a highly available IPsec setup based on some Linux instances and so on? I've probably seen keep alive D more often out of sync in an inconsistent state than seeing an actual failover happening. And AWS side-to-side VPN might be pretty opinionated and limited in flexibility, but that AWS takes this whole thing over for me makes my life just so much easier. And then finally, on the far right side, I see AWS Elastic Load Balancing. And this nowadays supports a wide variety of protocols, TCP, UDP, HTTP, gRPC. It terminates TLS, and especially the application load balancer is so flexible that it can even execute arbitrary code by invoking Lambda functions. And just a little less powerful, I would say, is the Transit Gateway, which is what we were using in our project. And let me explain you what this does. Yeah, I would say essentially, Transit Gateway is a router. You can have attachments, which is similar to like a cable that you can plug into that router. And similar to routers, it has a routing table, with the difference that you can actually have a routing table per attachment. And I've pasted here one slide from one of the great AWS reInvent presentations from last year on the topic of the Transit Gateway, where you can see, for example, that you can implement very specific routing scenarios. One is that, of course, everything can communicate with everything, a flat topology, or you can isolate different VPCs that are connected to the same Transit Gateway, for example, for shared services, VPCs, and so on. I won't go too much into detail here, but there's even a separate talk in the last time slot today in track 1, which will certainly go a lot more deeper here, and as well, of course, the other talks from previous reInvent. Yeah, by that, I think Transit Gateway does a bit more than just routing. In a normal router, you would implement a few things via firewall rules, via VRFs or whatever. I think Transit Gateway is a nice stripped down usable version of that. And this is implemented using AWS Hyperplane, meaning that it's super scalable and reliable and everything that we want. So let's look a bit better at like the different cables then you can plug in. So the different attachment types, you can attach VPCs to a Transit Gateway. This goes by deploying an elastic network interface. And I assume that the name Transit Gateway comes from the challenge of transitive routing that was before not possible via VPC peerings. And now as a Transit Gateway really deploys elastic network interfaces into our subnets, it can overcome that problem of transitive routing across multiple VPCs. What was also shown before in the slide was VPN. So the previously existing site-to-site IPsec services, they can be connected as well, so that you could connect your office network, or if you're not in the office today, okay, you have to find a different way to connect to your infrastructure now. Direct Connect also, if you make use of that, you can connect it to a Transit Gateway. And last but not least, which was released last year's reInvent, is that you can peer one Transit Gateway with a Transit Gateway in another region, so that those regions could communicate via this Transit Gateway peering. Yeah, and all of that, that gives me somehow serverless feelings. This router has an API. It's horizontally scalable, and especially somebody else fixes it. So I'm kind of questioning, are we calling this routerless? So far, this term isn't really in use. I think maybe we can change this with this talk with your help. But don't care. What this really means to us is that we can terminate yet another fleet of EC2 instances and replace it with a managed service by AWS. Why am I, but also we as EMnify, freaking out so much about networking functions provided by AWS? Well, I would say because networking is our product, or connectivity is our product. We implement a cellular connectivity platform for IoT devices. So our customers buy EMnify SIM cards and put them into their devices, be it GPS tracker, scooters, whatever, fridges. We don't really care for what they use it. And this is then almost globally covered. You see only a few gray areas on this map where we don't have a coverage yet. So no matter where your devices are used in the world, you get a connectivity via the different access technologies, 2G, 3G, 4G, but also those which you might have not heard yet, which are optimized for really machine-to-machine communication, low bandwidth, low battery usage, and so on. And also our pricing is a lot more adjusted to customers managing thousands of SIM cards instead of for myself having my own personal SIM card from a normal operator. And we support global IoT deployments in a lot different ways than traditional operators. If you imagine that you have a SIM card from an US operator and the device with this SIM card is, for example, roaming in EU or in Asia, then through the so-called home routing, all the traffic goes to US first. This is a concept how it is designed by the inventors of mobile networking, and that's what you will find in reality out there. So no matter in how many regions you actually deploy AWS IoT, for example, the closest AWS region is always the one closest to your network operator, which gave you the SIM card. This is, of course, not desirable for a global deployment. It's also not desirable to engage with tens of operators to pre-select the right SIM card, because you also don't know where your device will later be used, probably. So we, as EMnify, who are targeting really IoT use cases, have designed our system from the ground up in a distributed way. We deployed in multiple AWS IoT regions. And because this is not something that you can buy from a traditional vendor, we develop and operate all of that ourselves on AWS. To support our customers who manage thousands of SIM cards, sure, they need the possibilities for cost control, for controlling which networks these devices can access, and to get insight about like how much data devices are using, or to manage quotas. And then you have like our portal. Here is a preview of what we are currently working on, a lot nicer than what you will actually see later, our current state. But you can manage your IoT devices or your SIM cards, which provide a connectivity for IoT devices via our portal. But of course, when you're dealing with really factory processes, with other platforms that should integrate with, or where you want to integrate our connectivity contribution to your overall IoT product, and then of course we offer APIs that you can manage and integrate it with your own software. And we make the life of developers a lot easier because, for example, for SMS sending and receiving, you don't have to implement the protocols that are used in the telco world. But you can make a REST API call and we would deliver the payload via an SMS. And also the way back, we could deliver you via a webhook what was the content of this SMS. Similar usage data events generated by the connectivity system can be also streamed over into many, many different applications that you might have already in use in your environment. Secure connectivity is an important aspect because usually your fridge or your GPS tracker doesn't browse the internet. So why should it have free internet access? What you usually aim for is that devices can connect only with with your own private network where you run your application server that receives the sensor data, for example, or where you have your management infrastructure that might push out firmware updates, things like that. And it's often needed that also, you can reach out to the device, maybe log in to fix something, basically circumventing the NAT that is usually applied when you do it via internet access. And also as an additional security layer, it's definitely helpful to have an IPsec VPN over the internet because this tiny microcontroller in your IoT device might be using nowadays safe encryption algorithms, but it might not be safe for the future based on the compute power, and when in a couple of years the encryption algorithms aren't considered secure anymore, then you have at least an additional layer. However, the drawbacks of this is that in traditional telco environments, the setup and the recurring costs are in the order of thousands often per month, meaning you need a so-called private APN, and that's again how the designers of the 3GPP standardization have envisioned that it should work, and other things like for IPsec for radius, you always pay usually a lot of money, makes the setup complex, and it takes usually a longer while to deliver this. We at EMnify, we're thinking, what can we do in addition to the IPsec that we offer, of course, as well, but what can we do for customers that also run on AWS like we do, because IPsec from AWS to our AWS doesn't make so much sense to me, actually. So we were searching for how we can implement a new feature that we called cloud native connectivity. And we wanted basically that we secure the data up to our AWS deployment, where we run our infrastructure, so our packet gateways and so on, all the things that you need for a mobile core. And then we want to securely hand it over into our customers' VPC using AWS native features. And yeah, in principle, this private APN and those things, they are not needed because our system is from the ground up designed differently, that this is not an add-on, but this is the standard that you can offer private connectivity. Yeah, when we use an AWS native feature, it's usually highly available by design, and it's also available immediately in terms of via an API. And let me explain you for a short moment how roaming traffic actually works. So assume you have a SIM card or a device with a SIM card roaming in South America here, connected to the cell station, and it wants to send data to a server somewhere in the US. And there we have to actually split those two domains. On the lower side, we have the telco domain, and on the upper layer, we have kind of the internet domain. And yeah, we have peerings from our AWS deployment with carriers that transport all this roaming traffic towards us out of the telco world, so to say, into our AWS deployment. There we charge our customers, of course, for the traffic and so on, apply firewalling, etc., and then can send it to the internet or to a VPN. And yeah, this lower layer, GRX network, stands for GPRS roaming exchange. That's a private network actually between all the network operators worldwide, which looks like the internet, it works like the internet, but it's actually completely separated. And yeah, to provide connectivity for our devices globally, we are having the same setup where we establish peerings to multiple carriers in multiple AWS regions. So when we now think of how can we implement such a secure private connectivity, starting from VPN, which is something which we want to have something better. Private link is definitely one of the possible solutions. However, this limits the use cases. On the one hand, one way, it's that one-way connectivity only, like the devices would be only able to send data to the application server, but not the way backwards. And it's also TCP only still today. Yeah, the VPC peering, this would allow bidirectional connectivity. However, the scale would be limited, as the number of VPC peerings that we could establish is rather limited, in contrast to AWS's Transit Gateway, where we can connect thousands of VPCs actually to our Transit Gateway. So I'd like to walk you through how we have set up our Transit Gateway, not necessarily how you would need it in your setup, just that you get an understanding how we applied Transit Gateway to our own use case. Yeah, you go to the VPC section in the console, and then to Transit Gateway, create a new one, and you have a couple of options, not too many. And the result is that you have a regional resource which is automatically available in all availability zones. Okay, then we have, so to say, our router. Let's connect something. Let's connect our EMnify core VPC. And yeah, we create a Transit Gateway attachment. You have to pick which VPC you want to attach to its Transit Gateway. And yeah, don't forget to actually add a subnet in every availability zone. We ran into the problem once because you would later add just a Transit Gateway attachment to the routing table. And when there is no attachment in this AC, then you don't see any errors in the routing tables. Also, you would just see no traffic flowing, which is then, of course, a bit hard to debug. Of course, then we want to connect our customer's VPC, which goes, similar but different, because we can't just select our customer's VPC because that's in their account. We would first create a resource share using the Resource Access Manager, and then by this share the Transit Gateway with our customers. And now they have access to our transit gateway and they can create an attachment in their own account. And we see the result here. We see that the transit gateway owner is our account and the resource owner account is another account actually. So this attachment is owned by another account. Okay, we have now all these VPCs connected, but we don't have really routing yet. So let's add a routing table, the one that we apply to traffic coming from our VPC, so meaning packets traveling from the bottom up. And there in this routing table, specific transit gateway route table, so it's not the VPC routing table, we maintain a list of static routes, with the destination prefixes of the customers and then the actual attachment to which transit gateway should send these packets. And this is then really only associated with a single attachment, which is our own VPC and allows, from our point of view, egress traffic from the side of the IoT device, that the device can send traffic to the application, but not a single packet would find its way back. So of course we need to implement the other way as well. So there's a route table that we apply to customer attachments, which is similarly set up. And we see that here at the first row is our VPC attachment. This has a certain routing table ID, and below all the other attachments have the same other routing table that we apply to our customers. And with that, we have implemented this north-south connectivity. Devices can talk to only to the customer's VPC, but as we wouldn't expect that our customers want to talk to each other, traffic between our different customers' VPCs is of course not possible just because there is this separate routing table attached. To the final big picture about data plane implementation that I just described. So again, to recap, on the left-hand side, we have the IoT device roaming somewhere on the world using an EMnify SIM card, attaching to some mobile network, the so-called visited mobile network. Then via different interconnections, the traffic goes finally into our AWS account, into our VPC. There we process this. According to the routing table in the VPC, we forward it to the transit gateway attachment. There, the routing table of the transit gateway attachment is applied for this packet, and then the right customer account, the right attachment being chosen. And that's, for example, how an IoT device would send some sensor data into a customer's application server. So, that's already a nice implementation that we were able to do with that. There are two additional nice things that we can deliver using Transit Gateway. First of all, what AWS added a little later and what we have still on our agenda to implement, but plan to do soon, is making use of cross-region Transit Gateway peering. So as we have deployed our infrastructure to a limited number of regions, because we need to establish all these peerings to the carriers, we of course have a gap to our customers' deployment, which might be in a totally different AWS region. And this Transit Gateway cross-region peering would allow us to do this. The only change is that nowadays, at least, we would still have to manage the static routes in all the Transit Gateways. In last year's reInvent, they already mentioned something regarding dynamic routing between peered Transit Gateways. So I would hope to see this finally released at this year's reInvent, which will make our implementation a lot easier and more robust. The second thing is actually IPsec VPN. So there is still a huge customer demand for this because not everybody is on AWS. And the good thing, the good bonus of having Transit Gateway is that we can actually replace our previously used custom IPsec setups in Linux EC2 instances with AWS managed site-to-site VPN. Through Transit Gateway, this now became finally really usable for our scenario. Before it was not possible. And of course, the advantage is it has an API. So we can provision it via an API actually based on when the customer just calls our APIs, we forward it, so to say, to AWS APIs. It's highly available using BGP. We don't have to implement and automate all of that ourselves. And if it breaks, somebody else fixes it. And now that you know how this Transit Gateway connectivity is implemented, I would like to show you in a short demo how our customers can set this up. I have pre-recorded this earlier today because while you add this attachment, it sometimes takes a couple of minutes until it becomes finally available. So you see here on the left-hand side our portal with my personal test SIM cards and test devices. And I would start. So this test phone, this is what I had in my phone while I recorded this demo. We see here on the left-hand side the private IP address that it has. It is a Deutsche Telekom network attached. And this is really this Android smartphone that carries this SIM card. And yeah, let me show what the ISP is of this SIM card. Little unexpected, it's not Deutsche Telekom and so on, it's AWS, because the IP address used in the internet is our elastic IP address. So for the sake of this demo, I've set up a small VPC. And also, yeah, to make it as simple as possible, an EC2 instance just running an Nginx. And I would like to establish a private connectivity to this EC2 instance. So we copy the IP address, we try to access it, but yeah, of course, it's not possible. This is a private IP address. There's still no interconnection at all. And this instance doesn't even have any internet access. I can show you. We look at the transit gateway attachments. There's none yet. So yeah, there is no way that this SIM card can reach to an arbitrary instance in my personal AWS account. So going into our portal to the Cloud Connect, I can create one, pick the transit gateway, yeah, give it a name, and pick the region where my workload is running. So I'm in EOS 1. Then I need to figure out my AWS account ID, which is nowadays, since they refactored this scroll bar, this toolbar, easier to find. And then I need to add which IP prefix I want to route there. And there I just take my VPC CIDR block, paste it there, and click on next, double check, click on create. And then it says, yeah, I now have to accept the resource share invitation. So I go back to my account and go to the resource access manager. And then I see already, okay, there's one invitation pending. This is the EMnify Cloud Native Connectivity Transit Gateway. That's cool, that sounds expected. And I can review the details and I can accept the resource share now. Good, then I have this transit gateway now available. What we actually have to create is then an attachment. Go back to the VPC section in the console, downwards to transit gateway attachments, and then I create a new one. Pick the transit gateway. This is the one that was just shared with myself. Then the hardest part, of course, giving it a name. And then finally selecting to which VPC I want to attach it, as said, and attach it also to all subnets there. So then it takes a while. First of all, the acceptance is pending. So on our side, we have now something checking every 60 seconds for the attachment and accepting it. And this video was cut there. It usually takes a few minutes until the attachment is really available. We added a routing table of the VPC, add as a next hop the transit gateway, and then yeah, save the routes. And now we have basically established all the connectivity. And yeah, finally, we should be able to access this website. And if this were a live demo, I would be super afraid now if I mistyped something. Yeah, it takes a while even until AWS updates the VPC routing tables. But in just a second or two, you will see that it actually now finally, okay, could load this start page of this Nginx AMI by Bitnami that I have used. So we could now, yeah, set up the Nginx or PHPMyAdmin or whatever you might use in a real use case. Of course, this would be then usually used to deliver sensor data or whatever your application is. You see then here in our portal, the transit gateway being active and usable for your private connectivity. Okay, that's the demo from my side, I would now like to show you how we have implemented this, say, control plane, this orchestration layer that is accessible via our customer portal, via the REST API underneath, of course. And because we don't want to fire up Terraform, also when a customer wants to set up connectivity, this should be all automated by itself, triggers by the REST API call. So on the bottom, we see the data plane about which I was talking before. On the top, you see now this control plane. From left to right, our customer is making an API call, which is received by the API gateway. And then this calls our Cloud Native Connectivity API Lambda, which can look up existing CNCs using in our Aurora database. On the other hand side, if there is a request to create a new transit gateway, it starts a step functions workflow. So AWS step functions is basically a state machine which can, for example, call other Lambda functions. And in contrast to a Lambda, which has a maximum lifetime of 15 minutes, a step function workflow can live for around a full year. So basically, we kick off the first Lambda, which just shares our transit gateway with the given customer account. And then it really might take 2 minutes, maybe 2 hours, or maybe never the customer finishes to really accept the request and to create the attachment. And we call our accept attachment Lambda then over and over again by that step function until we finally see the attachment being created by the customer. If after 7 days, because of whatever reasons, the customer didn't create it, okay, we throw away everything, and that's also implemented via this state machine and step function, which is pretty nice. Then when we have accepted the attachment, we need to wait a couple of seconds until it becomes ready. That's again calling the Lambda function until it succeeds, because it requires that this attachment is actually provisioned by AWS before we can update our one transit gateway routing table, where we would have to add a destination prefix going to a certain attachment. So to finally conclude my talk, more and more serverless networking functions are available in AWS. That's nice if you're interested in this. That's nice if you have a networking centric product. And more use cases can now be realized in the serverless way through Transit Gateway, because the data path is taken care of by AWS and the whole thing has an API. In our connectivity platform, we made use of a Transit Gateway for establishing or for implementing our cloud native connectivity features. And this has both a fully serverless data plane and control plane. And therefore, we have a shorter delivery time for our customer and better stability. That's so far my talk. Just in case as we're all advised to stay at home, maybe you have some spare time and have since a long time planned to work on whatever IoT project, some Raspberry Pi that you might have been lying around since 2 years. If you go to emnify.com/devs, you as a developer can just enter your address and we would send you a SIM card that you could just use for playing around. If you do that, I'd be super happy to hear from you. I'm ST Gebert on Twitter. Interested to see what you have built. Thanks so far. Thanks for the interest.